Good morning, students. In this class, we will be discussing models for artificial neural networks. The simplest form of neural network can be possible with the one neuron only. Just for demonstration, what we have shown here is uh, one node. This is a neuron here, right? And it can have a multiple inputs from W0 to W 12,287. So this can be shown actually as a vector, right? So this vector can be of any dimension, right? Like from 1 to n. So uh, in single layer perceptron, we can just train any classifier, for example, a binary classifier, which can classify between dogs and cats. So we can feed an image into a vector form to this perceptron. What this perceptron will do, this perceptron will take a dot product uh, between the weights of the edges and the input vector x. So at first we don't know like what is the weight, what are the weights, and we can randomly initialize some value between 0 to 1, right? We can randomly initialize some values between 0 to 1 for every weight, and depending upon like how my weights are doing, I can fine tune as per my model labels. If I feed a cat and let's say the label for all cats in an image is 0, and for the label in dog in image is 1. Now if I feed an image of a cat, I am expecting somewhere here 0, right? Because I am expecting a label, predicting a label. So whatever the value that is having with the weights, I take the dot product of this in input vector x. I add some bias here. This bias is with this neuron, and then I will apply an activation function. So here this activation function is perceptron is nothing but it's a step function, right? If it is greater than 0.5, then it is 1, and if it is greater than 0, let's say it is 1, and if it is less than 0, then it is 0, right? This is how we can do it. Now the moment I feed some image which belongs to a cat, I am expecting here 0, and let's say the value that I am getting here is 1, right? So it means I am having some error here, because my prediction my I was expecting 0, but my model is predicting 1. So then I need to back propagate this error. I need to back propagate this error, fine tune my model. Fine tune my model means I will need to fine tune my weights, so that next time I feed the same image, I shall get 1, not 0, right? This is how what we can do. Just to remember, here we are using activation function, which is a step function, right? So before entering into how we can learn my neural network, I just want to introduce you with the basis functions. What basis function do is, for an example, if I have some vector, I can transform that vector into some other dimension, right, with the help of basis function, right? For an example, in my real image, in my input data, let's say here, I have two classes, red and blue. This is red and this is blue class. There are some samples somewhere here in two dimension. I can use my transformation function so that it can be projected into two dimension again. But now this in this new two dimension, these dots or red samples move somewhere here in the direction here in the space, and these blue samples somewhere move here, and this cluster of blue samples move somewhere here, right? So now what will what is advantage of transforming this space? The advantage is that at first I was not having a linear boundary here, linear decision boundary that can classify my red and blue dots, right? But now in this new space I can have my decision boundary, a linear decision boundary, and that can clearly separate my data set. Above that line there are red samples, and below that line there are blue samples. So what happens generally before applying any classifier in machine learning, what we do, we apply basis functions to it. So basis functions can be learned, or or we can apply them manually, right? We can apply them manually as well. So in neural networks, we learn basis function. I shall discuss like how to do that, right? Just for an intuition, like how basis functions can help. Not only we can transform from two dimension to two dimension, we can transform or project our data into higher dimension as well. For an example, if you in this image you can see that there is a rod, and if I have a pattern somewhere here in this glass, which is a kind of C pattern. I want to go, if both road and this glass is in two dimension, then it is not possible to pass this road through this curve. But if I transform my two dimension spaces into three dimension, that my road can move up and down now. And if I will move it, this is how it can move. Similarly, the other example is like, for an example, I have some red dots around and blue dots in a circle in this image. What I can do, I can just project my samples into three dimensions, such that my red samples bit elevated than blue samples, and then I use a plane to just by form a decision boundary, so that above the plane my red samples will fall, and below the plane my blue samples will fall, right? This is how you can see it. So here we can project our red samples bit elevated than the blue samples, and now because all red samples are above the blue samples, I can find out a plane, which can, that plane means linear decision boundary, and above this linear decision boundary you can see all the red points fall, and below the decision boundary all blue points fall. And if you see this decision boundary back into a real space, this linear decision boundary which was there in three dimension is actually a circle in two dimension. So with the help of basis functions, we can always find out a non-linear decision boundaries in actual space. Okay, that's just an intuitive understanding of what are basis function. So learn now from onwards, assume that your input, which was an image, is actually, you can either use a basis function on your input, or you can use directly use your input, right? So assume that the input vector is still an x, right? So here this input vector, why we have used theta here is just to make it in general that phi theta can be a can come through a basis function, or it is just a original x, right? It doesn't matter. So in general we have written it, so you can apply a basis function before applying any classifier, or if you can leave it either way, right? You can directly apply your classifier on the input itself, right, without applying basis function. So what my perceptron algorithm will do, I take a dot product with my input, right, and then I apply a function f. What my function says, if it is greater than 0, right, if my dot product is greater than 0, so here we have applied bias also, right? So if I expand it, so this w I if you see this is nothing but w transpose x plus b. So this in just an I'll this is we have written into a dot product form, and then we apply then we apply some activation function, which is a step function here. So my function, what it says, that if my dot product, which is scalar, is greater than 0, right? So this w transpose x plus b is equal to a in this notation, right? Because this a is nothing but this one. So if it is greater than 0, then I will generate +1, or I predict +1 as a label, and if it is less than equal to 0, I predict -1, right? So let's say I have because I'm doing only binary classification, I can put my two labels. Either it can be 1 0, or it can be +1 or -1. So here in this example, here in this demonstration or lecture, we have taken this representation +1 and -1, right? And my weights are these vectors which can have any value between 0 to 1, and x is nothing but it's an image or input features, right? So now this error function is what is this error function? We need to determine like what we need to minimize it. So as I said, that we can have two labels, +1 and -1, and I can predict right or I can predict wrong. If it is right, then it's okay. I don't have to do anything. I don't need to fine tune my weights. But if it is like if it is wrong, then I need to fine tune my weights. So we need to come up with some kind of error function. How to gauge that error? So that one thing is that I can just like error function would be a total number of misclassified patterns. So let's say I have 100 examples, and I just feed my 100 examples one by one and predict the label. Out of 100 examples, I found out that 60 images were like predicted wrong. So I say that in first when my weights are these, and when I started with some weights, and I say that when my weights are these, like my error is 60, right? Then I just fine tune my model a bit, and then I just do it again, and now my all predictions, like right predictions, are 70. So I have just improved a bit, but still not so far. So then I do it again and again and again. I will keep on improving such that I will predict all the labels correctly, whether it's dog or cat, right? So but how to do that? If I just, my error function is only a misclassified pattern, then it's like a constant error, right, for a given number of samples. And I cannot apply a gradient descent, because what my gradient descent says, I need to calculate a slope of a function, error function. So here my error function is piecewise constant, right? I cannot find out a slope anywhere, because either my slope is 0 right here, or my slope is undefined at these corners, right? Here my slope is 0. So this error function, though intuitively it looks good, but we cannot do anything with this error function, because I cannot apply my gradient descent, what we have learned in our previous class. And just to come up with this situation, what we will do, we will come up with like we should come up with an error function which should not be a piecewise constant but piecewise linear. What will happen, what is difference between piecewise constant and piecewise linear? So from here to here, this is constant, right? But if I make it linear, from here to here, linear here to here, and let's say then again it's linear from here to here, then it's linear here to here, then it's linear here to here, right? So then I say that it's piecewise linear, right? Then I say that it's piecewise linear. And then I can apply my gradient descent, because here every time I find out some slope, right? I can find out some slope, and based on my slope, I can walk into a direction where I can minimize my error, right? So this is the all like in perceptron algorithm. So we need to come up with an error function that can be differentiated, right? So now what we are having some dot product, right, in a perceptron, that we are gauging whether it should be greater than 1, or it should be less than it should be greater than 0, then it is +1, and if it is less than 0, then it is -1. So if I am predicting every time correct label, so it means my dot product is if I take a product of my W transpose X with my label, then it shall be always greater than 0, right? Because if my label is correct, right, if I'm predicting my cat, right, let's say that cat is minus +1, and let's say that my dog is -1. I have just given these labels. So I feed my x, which is cat, right? I feed my x, which is cat. Then my model has predicted +1, let's say, right? If my model has predicted +1, I will multiply that +1 with my label of a original label in a data set, and both are plus 1. So if I take a product of this plus 1, I will get plus 1, right? Now if I feed my dog image to a perceptron, right? If I feed my dog image to a perceptron, then my, let's say my model predict minus 1, right? And because the true label is also minus 1, if I take a product of these minus 1 and minus 1, I will get plus 1. So what I'm trying to say here is, if every time you predict and every time your prediction is right, and then you will have always a plus 1 of this product, right? The true label and whatever the prediction is, it is always plus 1, right? It is always a greater than 0 thing. So it means you can easily identify whether you are doing wrong. If it is not greater than 0, right, then it will be minus 1. So just to misclassify the error function, just to find out how many samples you have misclassified, here is this plus w transpose theta t, right? This w transpose theta. So this W transpose theta text Tn will always give me some negative number. Let's say for every time I am predicting wrong. So let's say I have some 100 samples and I have predicted 30 times wrong. So my the sum of this thing will be 30 and y minus 30, right? Because I predicted minus 1, minus 1, minus 1 for every wrong prediction. And then while I multiply this negative with this minus 30, so finally I will get an error 30, right? We have used this negative just to make my error positive, right? So then my error curve will look like this in the positive direction, which is above the 0. So this 0 is get multiplied just to make the quantity positive, overall positive, right? And now this is piecewise linear, and I can take a derivative of it, and based on the derivative, as we have discussed last time, what was the formula? We have some old value of my model of my parameters, right? So these old value of parameters, then we will take then what with these old value of parameters, what we do, we take a derivative of an error function, right? We take an a derivative of an error function. So this is my error function. I take a derivative of this error function. Derivative means derivative with respect to what? With w, because w is my parameter. So I take a derivative of this error function, and I take a walk in the opposite direction of this gradient. And when I say that I need to take a walk, I need to decide a step size. Let's say the step size eta. So I subtract with my old w, and this is my new w now, right? This is my new w. And then I will do this all these I will repeat all the tasks with this new w and update it as likewise, right? So this is what we have done here, and like uh, we are this is again the demonstration of like what is how gradient descent, like because this is piecewise linear and it is a convex function. So if anytime you will go somewhere here, you will just minimize it, right, some one day. So so now there is a small change, mathematical change here is that because you can scale your w such that scaling w will not change an error, right? So we can set the linear rate eta to just to accommodate this equation. So we are right. So what we can do, we can scale our w so that my eta will get to 1. My eta will get to 1, right? So just to all of you, just for your like information, if you see carefully, this negative get changed into positive. Why? Because my error function was negative summation of all misclassified sample. So how many number of misclassification are there? I take a sum of them, and then I was using negative, right? This negative when get multiplied with this negative it will convert into positive, right? And then this will come. What was my error function? It was all the misclassified errors. So it was like w transpose x into tn. When I take a derivative with respect to w, then I will get only this x and t. So this, so that's why this x, this theta is nothing but this is phi x, right? It's just a demonstration. It's just a symbolic notation. So phi is nothing but it's the input vector. So because I take a derivative with of my error function with respect to w, this w will go away because of a derivative thing, and it's a vector calculus. So now you will left with this theta phi t, right? So this is finally after taking, after plugging a derivative value, that is derivative value of error into an equation, you will get this, right? Fine. So after plugging the value of EPW here in the equation, you are getting this. Now what we are doing? We are just scaling our W, right? Because scaling W will not change my error function. So we are scaling a W such that my eta will get to 1, right? So how to scale this value? I just divide this whole equation with eta, right? When I divide this whole equation with eta, so what will happen? These both terms will divide by eta 1, right? So this is also divided by eta, this is also divided by eta, eta cancel eta, and now this I have just scaled my w with the factor of 1 by eta, and this is my new w, this is my new w, but new w will not change anything, right? It will, my error will be same. So now the advantage of this is that I can get rid of my eta in this updation rule of stochastic gradient descent. How you can see this? Because this is a, because you may not see any big advantage of doing it, but when you apply a gradient descent, the only thing you need to do is for every misclassified sample, right? For every misclassified sample, you just need to do this equation. What this equation says here is, for an example, you are somewhere here and this is your decision boundary of a perceptron. If this is a positive sample, if this is a positive sample, if means this is your x, right? And this is the value of a w. W means the vector of a the vector which is describing your hyperplane. So what you are saying, you are just multiplying this, just adding this x with w, because if your original label was +1, if your original label was +1, this then tn will equal to be 1, right? And then you can see only you what you are adding your x with w, right? You are adding x with w, and when you add your x your w, it means you are adding these two vectors, and when you add these two vectors, when you add these two vectors, then you can update your new w will be updated, and it will transform your hyperplane, and for every sample you will do it, right? For an example, for red sample, what we are doing here is this is, let's say, for red it is +1 and for blue it is -1. So now my x is this and my w vector is this black one. So because every time I have a positive sample, I need to add these two vectors. So when I add these two vectors, this is my new vector now. So this new vector, what will happen? It will tell me what is my new orientation of a hyperplane, and this new orientation of my hyperplane will be this, and this is my new vector w, right? This black vector w will come here somewhere, and this is my new orientation of a hyperplane, and I will do it for every sample one by one, right? So I have one by one, because we are running stochastic gradient descent. So we are we take one sample, we find it out whether it is classifying right. If it is classifying right, we leave it as it is. If it is classifying wrong, either we add it based on its true sample if it is 1, and if it is -1, then we subtract it from w. That's it, right? For an example, again for red, we need to add these two vectors. The new vector will be this. So this is new vector, and which will make classify my new orientation, because my w is always orthogonal to my hyperplane. It can always reduce an error, so you don't need to worry too much about this slide. So it can be proved that this updation rule will always minimize my error, right? So we can, it can definitely converge, right? If my data set is linearly separable, one or the other day I can always find out a hyperplane which will tell me like whether my all points are classified accurately or not. given that my data set is linearly separable. If it is not linearly separable, my algorithm will never converge and it keep on updating. For an example, right now, let's say I have two samples like this and two samples like this, right? Now I need to find out a binary classifier, perceptron classifier, which can help me to find out a linear decision boundary. But you can see that I cannot have any linear decision boundary which can separate it. So in this case, I will go for this. Let's say I start with this hyperplane, and then I will update it, then I will come to this hyperplane, then I will update, I will come to this hyperplane, and I keep on doing it. But my algorithm will never converge because my data set is not linearly separable, and it will go into an infinite loop of convergence, right? So this is a bigger disadvantage. So you can never know like whether I have converged it. If you don't know what is the characteristic of your data set, then it is really hard for you to find it out, like whether your algorithm is still converging because your data is linearly separable, or it is an infinite loop of convergence because it is non-linearly separable. So if you don't have any idea about your data set, like whether it is linearly separable or not, then you are in a really hard situation to find it out whether to stop the algorithm from learning or not. So for linearly separable data, you can have many solutions, right? You can have multiple hyperplane. Why you can have many solutions? Let's say you have linearly separable data. So these are the two. So you can have this hyperplane, you can have this hyperplane, you can have this hyperplane, and you can have multiple hyperplanes which can give you an answer, like a correct answer. So that's why for linearly separable data, you can have a multiple solutions, and solution depend upon the order of the presentation, right? For an example, if you start like this, first you take this sample, then you take this sample, then you take this sample, and then you take this sample one by one, then you can converge to one hyperplane. And if you start with this some sample like from otherwise, right? Let's say this is one, first you have taken this sample, then you have taken this sample, right? Then you may converge into a different hyperplane, right? Let's say this is first sample, second sample, third sample, and fourth sample. Then you may converge into a different solution. And it depends like from where you started also, that also matters, right? So the limitations is that you cannot generalize it for more than two classes. That is the limitation of a perceptron. You should remember this. This is the really important thing to remember here, is that you cannot that you cannot generalize for it for more than two classes. And perceptron does not provide probabilistic output. Either it give you +1 or -1, but you don't know like how good you are doing it. So if it is either it is right or wrong, it's a binary classification. But sometimes you may expect like at what probability is good, right? So it is fine, you are wrong, but with point a one probability you are wrong. So you are a bit sure like whether to take risk on that or decision or not. So some most of the time in which this neural networks, we expect a probabilistic output rather than a uh, this discrete output. Okay, this is all for this perceptron learning, and which is one of the variant in neural networks. And I will start with the second model, which is logistic regression, uh, afterwards. Thank you.